So good morning, everyone. I'm delighted to be here. Thank you very much for the invitation. I learned a lot of things in the past 2 days at least, so I hope that that will be the trend as we move forward. Before I deep dive into my own research, I would like to share with you a personal story, which effectively is the circumstances that led me to do the research that I'm doing. So about a decade ago, somewhat of a midlife crisis, I realized that I get more and more gray matter, actually gray hair than gray matter, that was the issue. And my ambition to make a Nobel Prize worthy discovery with my own hardware became slimmer and slimmer. And one way would be to sort of surrender to that and admit the defeat. But I didn't want to give up that quickly. And this story is really my attempt not to try to do it with my own gray matter, but actually to build a machine that will do that for me, right? So let me summarize in the first slide the goal of this research, and later on we will see how this goes. So imagine that we have some data from a natural phenomenon or maybe an artificial process, but we also have some knowledge which can be articulated formally as a bunch of equations or something of that sort, right? So we can mathematically articulate that knowledge symbolically. And the idea is to take both of these sources of information and to put them in this Nobel Prize machine, crank the handle, and off you go, you get a discovery. And it's nice to get a symbolic expression that may connect between the input and the output of some system or phenomenon. But ideally, I would like to also get a derivation, right? I would like to get something that I can celebrate as a substantiated or at least derivable discovery. And if all would go according to my plan, the inevitable consequence would be this, and the way that I was sort of envisioning myself was something of that sort. So I'm still waiting for a call from Stockholm, but maybe that will happen. Of course, you know, this is not only my own effort. There are many talented researchers that have been supporting that. And although we don't have here Yanis anymore, but also generous funding agency, so DARPA, thank you very much, and others. So let's look into one of the basic questions we may ask ourselves: what is science? And in my mind, science is our quest to bring some understanding to the natural world through observation and reasoning. And I emphasize and reasoning. This is something that also René Descartes was putting forward, that we should not only rely on empirical evidence, we should also put some emphasis on deductive reasoning. And we all, I believe, agree that the scientific method that has been established by these two fathers of scientific or philosophers, in a sense, René Descartes and Francis Bacon, was transformative to mankind in scientific terms, but also for socioeconomical growth. And the beauty of the method is that it provided a practice for us to come up with substantiated discoveries. And for those of you who may, I'm sure that you all know that because we do that on a daily basis, but we start with a question, we then perform a study, we try to understand what has been done around that question, we then form a hypothesis. We need to test our hypothesis. We do that, we assess the results, and then we run and publish what we managed to discover, and the cycle continues, right? Now, despite all good intentions, there are recently some increasing evidence that the scientific method is going out of steam. And when we ask ourselves what is going on, right? So the rate of emergence of new discoveries is slowing down, and that can create a significant stagnation for economic growth. You can see this graph, for instance. There was a stick here yesterday. Here it is. while we keep on investing in research scientists, or we keep on bringing more and more scientists to the table, the research productivity is actually going on a decline. And there are different economical measures to establish that. And so you can argue whether this is the right measure or not, but there are a growing number of studies that support this said reality. The great Dirac stated that it is now more challenging for first-rate physicists to make second-rate discoveries than it was previously for second-rate physicists to make first-rate discoveries. And maybe it is just so happened that all the low-hanging fruits of science were already plucked, and we are just left with whatever is really high and maybe beyond our human reach. Now, on the other side, if you would like to be a little bit more optimistic, there are many reasons for us to believe that we can overcome that crisis. So we do see that many of today's challenges can no longer be challenged by a single scientist. You can see huge centers like CERN. So Atlas lifted the entire universe in his arms. That's not, these days are gone. We need to collaborate. We need to collaborate flexibly at scale. And when we do that, you can see some nice evidence like Wikipedia, Linux, other open source, and Foldit, and so forth, other projects in which we see that when we do hold hands, we can actually do remarkable things. Recently, the notion of collaboration, not only between humans, but between humans and machines, or even machines and machines, has become more and more popular, and that sort of makes sense. So that comes in our favor, trying to challenge that stagnation. We see about 6 orders of magnitude increase in computational power between 1991 and 2015, and emergence of new AI capabilities. So all of that gives us some hope. When we look into the hierarchy of cognitive function, and there are different ways to come up with that taxonomy and to figure out what should be at the very top. There is another taxonomy which is called the Bloom taxonomy. Typically, you would like to put on the lower part the more basic cognitive capabilities, and then as you climb up, things that requires more judgment and consideration. In the past few years, there was a big question: what should be at the very top of this pyramid? Is it creativity, or is it discovery? And lately, maybe the answer has become more apparent, right? We see how creative large language models can be, but when it comes to discovery, and that statement was made yesterday, and dynamical systems and so forth, we see that these systems still struggle somewhat. And my claim is that discovery is a harder bar to meet, because creativity can happen in a vacuum, right? You can do whatever you want, and that will be somewhat creative or less creative, but there's no bar of meeting observations or other physical constraints or other constraints that makes it harder, and therefore discovery requires a somewhat higher bar to be established. So when we talk about discovery, I particularly work on mathematical models. What is a mathematical model? In my mind, it's a mean to provide a consistent link between input and output of a system or a phenomenon. When we come to the art of crafting such models, we typically make some choices or compromises between the complexity of the model and how realistic the model is. There are other compromises that we can make, but on a very high level, there are really 2 schools of discovery paradigms or mathematical models. The first is, of course, the first principle school, and I believe that many of you here are actually coming at least from that angle. And then we have the other side, which is the more data-driven, empirical, or phenomenological models that are just driven by the data. And we can surely say something positive and negative about each of them. So when we look into first principle modeling, we have here all these giants, and again, I was imagining my own picture somewhere in the middle, talking about those Nobel Prize aspirations. But the beauty of the discoveries that these guys have made is that they are extremely universal. And if you take, for instance, Maxwell equations, these are 4 very, very compact equations that tells you everything you ever wanted to know about electromagnetism. And the beauty of those 4 relations, they hold here, they hold on the moon, but also if you take an inertic system, right, and you take Lorentz transformation, they would still hold valid, right? So it's amazing how efficient and compact and elegant those relations are. However, you may see that it may take some time to come with such reveal, and definitely a lot of talent. And our role model is Marie Curie, who, again, we are in the business of Nobel Prizes, not prize. She was the first one to get 2 rather than 1 Nobel Prize. So we hope to follow her footsteps. Now, on the other side of the fence, we have data-driven approaches. And again, if you don't read the small print, we are trying to come up with a link between input and output of some system or a phenomenon. However, the small print typically says with a particular functional form. And it's not that everybody are idiots and they deliberately coffin their hands and legs with a specific functional form. There is a good reason to do that because we choose those functional forms to be such that are computationally exploitable. Now, when is it efficient? When we have tons of data, then we can definitely think about learning. When we have no knowledge, there's no good reason to favor one functional form over another. However, I believe most of us would agree that these models tend to generalize quite poorly. And of course, if I came up with the functional form before I even saw the data or heard about the knowledge, I cannot expect to look into the functional form and come up with some interpretational insight about the underlying phenomena. Now, when we talk about data, we need to bear in mind that not always we have the privilege of abundance of data. So here is one example when data or experiment can be quite risky. Now, it can be even worse, right? You may need to go to a remote location and collect the data. You may meet some of the local residents and have to fight over the spot you picked up. And not always you have the upper hand in the story. Now, it can even be worse. You may think that couldn't be worse. It can be worse. I will now read you a complete chapter of a book. I hope that you're up to it. I don't know whether you ever heard a complete chapter, a book chapter in a lecture, but let's do that. It will be from Connon's book, Why String Theory, and it goes like that. There is no direct experimental evidence for string theory. End of the chapter. Sometimes we don't even have data at all, right? So we need to shift a little bit, to gravitate a little bit also to the small data or no data even scenarios when we come into the art of forming mathematical models. To trash a little bit more, at least conventional machine learning, we can ask ourselves what limits standard method. So if imagine that the gray line is describing some behavior of a system, and I try to build this model, the dashed line. The first thing that I will do, if I can, I will bring data. So here I am. I'm stitching or amending my model to the data I have. It looks okay. Probably we can do better. Let's bring more data. That trick seems to work. So let's repeat that over and over again. So bring some more. So we condition our model to the data, and okay, we got something, right? We may be happy about it or less happy. To be honest, I'm not very happy about this part because I wanted to have a better prediction at the very end. So let me bring the heavy gun, right? So now I will bring my better stapler. Here it is. And despite bringing a lot more data, it may help me to interpolate better, but I will not extrapolate better, right? So that's a known issue with many machine learning or data-driven approaches, because at the end of the day, I will get stuck with very little improvement, if at all, to my ability to extrapolate. And the reason is because effectively, these two functions in functional spaces are very different from each other. Yes, we force them to hold hands at specific locations where we have the data, but outside that, they can diverge indefinitely. And unless we do something about it, if we insist to have two very, very different functional forms, we may not stand too much of a chance in doing that. Now, trying to put everything together in terms of contrasting the two schools, it's not that we have a definite winner, right? I trust a little bit more the data-driven approaches, but they have their advantages. Now, if some of you that still, that do have glasses, if you take off your glasses, you'll notice that wherever I have green in one side, I have red on the other side, independent of the category, right? So it's sort of, and then apologies if any of you is colorblinded. You may see that there seems to be some notion of complementarity between these two classes of modeling, and that brings us to a question: should we derive or let the data drive? And of course, the answer is why not trying to do both if we can, right? Now, that brings us to symbolic model discovery. So how can we overcome this fundamental issue with a fixed functional form? Let's try to work in a free-form proposition that will enable us to be much more rich in terms of the classes of functions that we can describe. But obviously, that sounds very naive, right? Because if I look into a mapping between a set of point to a set of point, there are infinitely many mappings that will do the trick for us. And we have to impose a little bit more of structure or preferences to make it happen. So one approach is to say, okay, of course, I would like a mapping that will fit the data, but I also look for the simplest one or some mapping that honors some other virtues that I would like to honor with respect to my model. So our first attempt in this was to come up with a symbolic regression approach that is not genetic algorithm-based, but formally, deductively, or if you want, declarative proposition. We define a grammar, and in that grammar, every meaningful mathematical expression is a sentence in a formal language. In our language, we have three elements. We have operators, you see them in green, plus, exponent, division, sign. We have variables, you see them in orange. And then, of course, you have coefficients or constants. And what we are trying to do is we can encode the grammar as a set of constraints, and we then do a free-form search for both the functional form and the coefficients, the parameters that we are trying to do that, minimizing the complexity and trying to honor the data. We can write this formally, right? So if you would like a little bit of equations here, f would be my symbolic expression. I'm trying to minimize the complexity of that expression, subject to the fact that when I estimate my symbolic expression at specific data point, I get something that is close to my data in some noise model. And of course, I would like to enforce that my model is syntactically viable, so I cannot write something like x times division plus 53. That's not a valid statement mathematically. And with that, I can try to see how far I can go, right? So that was the first attempt. Now, going back in time, when Galileo was 25 years old, apparently the guy was studying medicine, and he was sitting at the Cathedral of Santa Maria of the Assumption in Italy. And he noticed that the chandelier was swinging at the same rate, independent of whether it had a, well, we have here, independent whether it had a large exclusion, right, or a small one, right? And at the time, he didn't have an iPhone or whatever to time it, so he was actually using his own pulse as a pacekeeper. But that fact intrigued him, and thanks to that, he actually came up with the invention of the pendulum watch. But we would like to figure out what's going on. So let's do an experiment that relates to that. We took a wave pendulum. So this is a view from above. We have here multiple bulbs connected with links of different lengths. And this is just, again, this is a photo taken from a phone, right? It's not a professional aperture, as somebody said yesterday. This is a mathematician's experiment. And what we would like to do, other than hypnotize you, we would like to figure out what is the fundamental equation that governs the period time of these pendulums. So we fed the data into the system. Actually, we took only, I believe, 18 data points. So when I talk about small data, I really talk about very small data. And after a bit of grinding, at the beginning it took half an hour, now it takes far, far less than a second, we got this expression. And for those of you who are familiar with this expression, or somewhat, the important element is that we got this relation, that the square root of the link length is governing the period time. And then we have this constant pi over square root of g, which actually was very challenging to achieve. The system insisted that this is a 1. And after we calculated what it is, it was 1.002 or something like that. Given that the data was very noisy, we had to do multiple periods. That's the reason you see this, the difference between the jth period and the ith period. And only then we got enough statistics to come up with that discovery. But the nice thing about this expression is that you have an immediate way to interpret how the pendulum will behave if you're going to change the mass. How it will change? It will not change. The mass is not really part of this equation. Or if you change the link length, or if you do change something else. Now, equally, you could say, oh, let me bring my favorite neural network and train it and get something that will describe me the period time. And when we think about a neural network, we can actually write it also in somewhat explicit form, right? So I can take my layer, multiply it by weights, sum it, and add my biases, run it through an activation function, take that new layer, multiply it by weights, add bias, and so forth, right? So we can explicitly write this very large term, and obviously you have very little interpretational insight looking into those weights or biases, trying to figure out what's going on, right? So at the very least, interpretational insight would be one advantage, but also I would argue that this expression would be more generalized in many cases. Now, we took Feynman's lectures on physics. He derives 100 relations in his lectures. And we said, okay, let's see which one of them we can discover. We managed to discover 87 out of them, but also 2 extra problems from Jackson's book, and I forgot the other book. And the nice thing is there are other systems that do similar things, right? So there is a system called AI Feynman that would require 100,000 points to make such discoveries. These discoveries were made mostly with 10 data points, right? So it's a day and night in terms of how much data you need in order to make such discoveries. And also robustness to noise. We will talk about it later. Now, that brings us to the next step. So again, another historical anecdote. Leverrier was engaged in trying to understand some systematic discrepancies between what he calculated to be Uranus' trajectory and what the observations really provided. And Of course, he could have just swept it under the rug and say, oh, measurement error, let's have coffee at the nearest Starbucks. But he decided not to do that, right? He was trying to figure out how come that these discrepancies came about, and being more leaning on the belief that Newton's laws are somewhat correct, he came to the conclusion that there must be another planet that we cannot see that create these perturbations, right? And after he concluded that, he wrote a letter to his friend at the Berlin Fraunhofer refractor, and the evening that letter arrived, they pointed their telescope, and within 1 degree of error, there it was, right? They discovered Neptune, right? So again, putting some more trust in the deductive logic side can sometimes lead to discoveries. Now, if we would like to contrast the two sources of information, let's see what they can bring to the table, and then maybe be a little bit more considerate about the use, right? So when we talk about data, data is very local. We even use the term data point, and when we say data point, we refer to geometrical point, because we don't really know what's going on epsilon away from that geometric point. We would like to believe that things are smooth and so forth, but we actually have no clue. On the other side, when we look into knowledge, so for instance, I can state something like, for all x's, y is larger than 17. I now stated something that is true for the entire universe, right? No matter to what x you will go, that statement will hold. And that was actually, it's a lot of strength, but it can be even a challenge, right? So if some of you are familiar with the AI winter, where we try to build rule-based systems, that attempt failed. And it failed because many of the rules were very, very universal. And at some point, they may look reasonable, but further out, they may contradict each other, and then the whole thing broke. So knowledge can be very global, maybe too global. We need to be careful with that. We also trust data to be noisy, but on the other hand, we need to acknowledge that knowledge can be incorrect. Newton laws of mechanics are incorrect. We know that. Actually, it goes even further. Einstein laws of relativity are incorrect. They are not consistent with quantum mechanics, which is incorrect because it is not consistent with gravity. So although we think that we have established everything, the very foundations of our science is not there, right? So there's still a lot for us to discover. Data can be sparse. Equivalently, your knowledge can be incomplete. You may not have all the required axioms in order to derive a relationship from A to Z. It can be expensive to acquire data. I showed you some examples, but equally it is painstaking to articulate and curate knowledge. The connectives we use with numerical data are arithmetic operations. The connectives we use when we talk about symbolic expression is typically logical inference operators. So just as a quick refresher for those of you who are a little bit more removed from the field of formal logic, we have the notion of axioms. These are assumptions that we take for granted. We assume that they are hold correct without any proof. Literals are propositional variables or their negations. Logical connectives are effectively symbols that connect between different propositions to form more complex propositions. So you can look into a conjunction, disjunction, a refutation, implication, equivalence, and so forth. Logical inference, such as resolution, induction, refutation, and so forth, are means for us to take several clauses and then deduce a new clause. And theorem is effectively the final statement we get at the end, where just before we write the QED, and the proof is the way to get there, right? So I hope that you're all familiar with that. I just wanted to refresh the terminology. Now, our first attempt was really to build this symbolic regression framework that had variable, constant, and arithmetic operators, which is nice, but it's really still a kiddie toolkit where we can have a much larger toolbox of elements to work with, right, if we bring the logic in. Now, there is a distinction between inductive and deductive logic. There's also a notion of abductive logic. We may talk about it at the end if we have time. Inductive logic is we start with observations, and then we identify patterns, we form hypotheses, and then we try to see whether it is consistent with our theory. The opposite direction is deductive logic, where we start from the theory, and we make hypotheses, we make observations, and then we confirm our results. So our second attempt, the so-called AI Descartes system, had the following ingredients, right? So we start with some data, we have grammar and modeling primitives, and then we bring everything into a symbolic regression system. It can be any other generative AI if you want a mechanism. We get several hypotheses, not one. Now we would like to shuffle them. Maybe now they're ordered by complexity or they're ordered by how well they fit the data. We may want to shuffle them differently, but the interesting part is so far I didn't use my knowledge. So let's bring the background theory, conservation laws, symmetries, invariants, what have you, right? Let's bring all of that, articulate that formally, and bring it into a reasoning engine, right? So there are so-called automatic Turing provers that can do the work for us. And they would do one of two things, right? So if my background theory is complete, to be honest, I don't really need any data. I can derive the desired expression from A to Z, right? I can derive it fully, and I will end up with my derivation. So that would be the ideal situation, but again, we don't really need data. How often do we have all my background theory? That's another question. Often that's not the case. The other thing that we then introduced was effectively, can we talk about distance from a derivable form, right? So imagine that I have conservation of mass as some manifold, and conservation of energy as another manifold, and there is a manifold or submanifold in which the two are interconnected, but I didn't bring conservation of angular momentum or some other important symmetry. So I didn't resolve the intersection of all of those theoretical symbolic expressions into a single point expression. I still have many possible things that would satisfy both of these important axioms. And so I would like to ask, if I have now one hypothesis that came from the symbolic regression, and I have another one, can I assess how far are they from a symbolic, from my background theory, right? From the intersection of my background theory. And we came up with a notion of a continuous measure of the distance from a derivable form. And with that, you can now reshuffle, you can reorder your hypotheses, not only by how complex or how well they fit the data, but how well they fit the knowledge or the theory. And then you can hopefully get a substantiated discovery. So let's look into, this is just explaining more or less what I described earlier about the background theory manifold and another manifold of the hypothesis and effectively establishing the distance between them. There are different ways to go about logic. So we were using dynamical differential logic for that purpose, which is based on the cylindrical algebraic decomposition or Collins decomposition, for those of you who are familiar with that. On a very high level, descriptively, imagine that you have m different functions that go from Rn to R. These are those Fi's. Each one of them can be true or false in two different sides. You are looking for the decision boundary where they are equal to 0. So let's say this is F1, this is F2. Now I segmented my space into several sections. In each section, the sign of those f's is consistent, can be true and true, or true and false, and so forth. And then effectively, I can check those sections, right? So that's really on a very high level. This is one approach. There are many other approaches. The beauty is that while we think about logic typically as set logic, which is very binary, we can actually think about some geometrical interpretation of logic, which is useful. I'll go quickly about a few examples. So we have an example from Kepler law of plenary motion, Langmuir absorption equation, and then relativity. So for those of you who should still remember Kepler's third law of plenary motion, the period time was proportional to the semi-major axis d cubed. We have the masses of the star and the planet on the denominator and the square root about all of these. If you ask yourself how you spoke about formal logic and like axiom, how does it look like? So here is an example of how background theory can be articulated. And here we took 3 different data sets. The first one was actually the original Tycho Brahe data set that was, I believe, 1609, that Kepler was using to come up with his own discovery. Then the NASA exoplanet data set, another binary star data set. The first step was just a symbolic regression. You get multiple hypotheses, right? And you may favor them by how well they fit the data. The next step is to bring the reasoning. And then you see that we are reshuffling them. And some expression actually goes further up. Maybe the next slide is more clear about that. Sorry. So if I would only trust the numerical error, I would favor this really horrifying long expression, right? I would believe that this is the best model for that. But given that we now have a new measure, we have this derivability, this continuous measure of how close it is to the theory, I may want to favor the model I have at the bottom, which look almost perfectly correct as the one that was discovered by Kepler. Actually, Kepler didn't discover both m's. The small m was negligible. But you can see how this notion of contrasting with the theory can help us sometime. Langmuir absorption equation effectively tried to see, to assess how gas is contracting a surface as we increase the pressure. Here we wanted to incorporate more. We said, okay, we may know something about the functional form, not only some axioms. So we may want to say that I don't really care what would be the expression, but I do know that I want it to be monotonically increasing, right? So I can encode something like that as well as part of my background theory. And then we can take data, and we took the real data he was using, and you can come up with multiple models. They may all fit somewhat the data, but only one of them would actually, or one of them will be closer to the theory. Actually, the one that we found was exactly, was completely provable, and that was number 2, I believe, F2 and G2. Further, we know that we may experience time differently, whether we are in a stationary or an inertic system, due to Einstein. We may want to contrast different background theories, right? So this is another thing you can do. You can come up with Newtonian set of axioms, or with Einsteinian or relativistic, and see which one of them would be more consistent. And that was the exercise we did here. Obviously, we cannot exceed the speed of light. So the second postulate here of Newton, which makes sense, you are going on a diagonal, it should be v squared plus c squared, but you cannot exceed the speed of light, it cannot be more than c. That was really the distinction between the two, and we managed to see that. But I do want to talk with you about something more, and just being conscious of the time. So all of this you can find in the AI Descartes paper. We would like to take things even one notch further, right? So it's nice to bring the theory, but there was still a limitation in the way that we did it. So taking a big overview, if we spoke a little bit about neural networks. In neural networks, we have a fixed form. We just tune a little bit the parameters and hope that something good will happen. The next step was saying, oh, let's go with free form, functional form, and we can come up with any construct. So we find both the functional form and the parameters. Next step was the AI Descartes, where we took some symbolic regression expression, and we also make verification or validation with the theory. But how nice it would be. So maybe the limitation here is I have to come up with good hypotheses just from the raw data before I validate them with the theory. It's a limitation, right? How nice it would be if I can come up with very little data, not enough to come up with a hypothesis even, and very little knowledge, right? I would have maybe 2 axioms, but not, I don't know, the 10th that I need in order to fully derive something. And I would like them to sort of meet somewhere in the middle, right? To make a discovery that neither of them can do independently. And that's the AI Hilbert work that is in print now, if Nature comes. So effectively, we try to come up with a unified framework where we try to, it will be an optimization problem where we minimize the compatibility with the theory, the data fidelity, and the complexity all together. And we are looking into implicit functions or functions that we discover. Fitting the data, we all know how to do that. No need to talk about it. Finding measures of complexity, I'm sure that there are many, many interesting ways to go about it. But the compatibility with the theory is really the interesting question here. And in this study, we decided to go with articulation of background theory as a semi-algebraic set. So effectively as a collection of multivariate polynomials, equalities and inequalities. And there is so if you ask yourself, if I now give you x1 to xn, whatever it was, and I ask you, does these values satisfy all of these polynomial equations, you can actually check. You plug it inside and see whether all these equalities and inequalities are being satisfied, and you can be happy about it. The opposite question of infeasibility, or to tell me nowhere you will find such an assignment of values that will satisfy all of them, is an NP-hard, decidable but NP-hard problem. Due to Hilbert's genius, I think it was his 17th problem, he came up with something called the null Stellensatz, which effectively, almost like a magic, enable you to solve this problem under mild assumptions on the degree and so forth in polynomial time, right? So this is really real magic, because for those of you who ever worked on logic, the showstopper is that logic is combinatorically expensive, and very quickly you get to a point that you say, okay, we simply cannot do that, right? So that big bottleneck hopefully is resolved. There is an evolution of the null Stellensatz, which is taking that over the reals, which is called the positive Stellensatz. And okay, I don't have enough time to go into that, but the essence of that is that you can come up with a so-called certificate of probability, which is a sum of square of polynomials. These are multipliers of our equality and inequality polynomials that provide us a certificate. Maybe in the next slide, I'll spare you. You get the bigger picture. So here are some of the axioms that I had articulated in polynomial terms. Here is the discovery on the top in an implicit form. And this is the so-called sum of square certificate that effectively provide me a proof of correctness of my derivation, of my discovery. So you get that. Here is the complete picture of, you bring background theory. You may actually incorporate deliberately or non-deliberately incorrect background theory. Again, we have to be robust to that, the same way that you would like to be robust to noisy data. That creates a polynomial program that can become a semi-definite program for computational reasons, and then you get your discovery and a proof of derivability of that expression. Some quick examples, so we can do that for differential equations. Here is a simplified version of a Navier-Stokes equation. Here are some of the background theory component. Here's the discovery. I will be quick here because I know that we need to move on. Relativity, so here is this monstrous radiation gravitational wave power equation. If you notice, some of the terms here are quite scary. We have tensors, we have a third derivative in time, and that can be discovered. I mentioned all those manifold that cut itself, so you can see that, you can even visualize that. We managed to get as close as 2 years ago in terms of Nobel Prize. So there was a Nobel Prize to Bell, not Bell, but actually the experimental work that assessed, that provide bounds for correlations of measurement of multi-particle, multipartite system that obey local realism, effectively refuting that, not only the GHZ inequalities, but also more sophisticated. This is like 9 pages of write-up to prove that, typically. So let me hopefully wrap up. The classical scientific discovery paradigm, we typically generate hypotheses from theory, and we make experiments with data. What we see a lot recently is many propositions to come up with data-driven discoveries of expressions. What we did in AI Descartes was actually to swap the order of the classical one. We form very similar hypotheses from data, and we assess it with theory. And what I hope AI Hilbert is really doing is combining 2 steps of hypothesis generation and hypothesis testing. Does it both at the same time. Now, back to the big question we had, can we scale the scientific method? Can we avoid the stagnation? To do that, we must disrupt the way we think about the scientific method. And we need to go beyond using yesterday's algorithm on tomorrow's computers. We need to come up with methods that offer us models that are universal, derivable, which is more than interpretable, that can deal with small and noisy data, but also with incomplete, inconsistent knowledge, and ideally simultaneously bring them all together. This is not the final word, right? So this is just a step towards trying to do something like that. If you're interested, we have open source code, so you can get your own Nobel Prizes if that's something that you desire. The royalties is very cheap. Just buy me a beer if you get a Nobel Prize. And since we are at the, okay, maybe, so this is what we do, right? Instead of hypothesize and test, we remove that and come up with a single arc of hypothesize or whatever it is. But I would like to just finish up with this epilogue. So Nobel Prize machine checked, right? I hope that you agree. We are at the Fields Institute, right? So what is my next big dream? Is to get a Fields Medal. And there is one problem. I hope that probably some of you can see I'm above 40. And that will be the solution. So we're going to build a time machine, and then we will do that. Thank you very much for listening.